Hello, I Anand Jain from Hanumangarh, Rajasthan welcomes you to your favorite Shridevi Classes YouTube channel where we inculcate interest and confidence in science and engineering subjects. Today in our playlist, Basic Electrical Engineering and Class 12th Physics, we'll understand RC series circuit in our chapter Alternating Current Circuits, and we'll understand that in an RC series circuit, voltage of resistance is in phase with current phasor and voltage of capacitor lags current by 90 degree, and phasor summation of resistance and capacitor voltage would have a certain lag angle between 0 and 90 from current phasor. And we'll also understand the concept of impedance, which oppose flow of alternating current in RC series circuit and demand proportional voltage for current flow. So let's start RC series circuit in alternating current supply. A pure resistance of R ohm and a pure capacitor of C farad are connected in series to a sinusoidal alternating voltage. Now this circuit is known as RC series circuit in AC supply. When we apply sinusoidal alternating voltage, a sinusoidal alternating current of same frequency but leading voltage by a certain phase angle will flow in this RC circuit. Now in series circuit, the current of resistance and current of capacitor is the same. Let this current is capital I. When the same RMS current capital I passes through this RC series circuit, the RMS voltage across resistance is VR, and this VR is product of RMS current and resistance, and this voltage is in phase with circuit current, whereas voltage across capacitor is I times XC, where XC is known as capacitive reactance of circuit, and voltage of capacitor lags current by 90 degree, and the phasor sum of resistance voltage and capacitor voltage is over supply voltage. And for this circuit we have to find out relation between RMS voltage and RMS current and the phase difference angle between applied sinusoidal alternating voltage and current flowing through the circuit, and for that we'll use phasor approach given by Standmates. In phasor analysis of RC series circuit, R operator is a real operator. It won't have any imaginary or vertical component. In rectangle form it is R plus J0, and in polar form it is magnitude R and angle 0 as shown here. Whereas current limiting property of pure capacitor is known as capacitive reactance, and capacitive reactance is minus J type, and its position is on vertical line in downward side in minus J direction, and its polar form is XC angle minus 90 degree as shown here. And in phasor diagram representation, in alternating sinusoidal supply circuit, current and voltages of resistance, capacitor or supply voltage all are phasors, and phasor are represented by rotating vector. And to make analysis simpler, rotating current phasor is considered in such a way that its rotation get freezed when it is at horizontal reference position as shown here, and when current is at horizontal reference in this series circuit, the voltage of resistance come along resistance line in phase with current as shown by this wave diagram. Orange wave is wave of current and red wave is wave of resistance voltage, and both are in the same phase, whereas voltage of capacitive reactance come along capacitive reactance line, and we see lag current by 90 degree as shown here. Current is shown by again orange wave, and this blue wave is voltage of capacitor. We can prove this by mathematical analysis too. In a series RC circuit, current of resistance and current of capacitor is the same, and that circuit current can be taken as a reference phasor, and it is considered at horizontal reference with T0 instantaneous magnitude as 0 and standard sinusoidal reference trigonometric equation as I equal to Im sin omega t. And resistance operator got only a real component, no imaginary component on vertical line. Then voltage of resistance in phasor got its position along R line in alignment with current phasor. So in resistance part, the current through resistance and voltage across resistance both are in the same phase, and this voltage of resistance is I times R. As time passes, these phasor of current and voltage in alignment rotates in anti-clockwise direction with omega angular velocity, and after quarter cycle they attain their respective peak positions. Current will have peak magnitude on vertical axis projection, and voltage also got peak magnitude, and further rotation of phasor reduce their magnitude, make both current and voltage after half cycle instantaneous value is 0, and after that current change its direction and voltage reverse its polarity, attain negative peak, and one complete rotation will generate one complete cycle. So this phasor diagram and this wave diagram both represent the same thing, and we can say the phase difference between circuit current and voltage of resistance is 0. Similarly, we can explain phasor relation of voltage of capacitor and common series circuit current, and once again, as current is common in series circuit for both resistance and capacitor, rotating current phasor is taken as a reference, and its rotation is freezed when it is at horizontal reference line, and its t0 instantaneous value can be taken as 0 as shown in this phasor diagram. And when current is at horizontal reference, the voltage of resistance come across resistance line in phase with current, and capacitive reactance, property which oppose current flow across capacitor and demand proportional voltage for current flow, known as capacitive reactance, and capacitive reactance is minus J type, or its angular position is minus 90 degree as shown here. So voltage of capacitor will come across XC line, and from that phasor diagram it is clear that voltage of capacitor lags current by 90 degree as shown in this wave diagram also. That means current peak will occur before positive peak of capacitor voltage, and every identical phase instant of current leads the similar phase condition of voltage by 90 degree. So RMS voltage of capacitor lags capacitor current by 90 degree, and RMS voltage and RMS current got a relation. Capacitor voltage is RMS current multiplied by XC or capacitive reactance, and for omega radian per second angular frequency, C farad capacitor got capacitive reactance XC as 1 over omega C. And as clear from this phasor diagram, the zero instantaneous position of current occur 90 degree before the same zero instantaneous position of capacitor voltage. That means current leads voltage by 90 degree, and at t equal to 0, current got instantaneous 0 magnitude and capacitor voltage got negative peak as projection on vertical axis. And as time progress, current attain positive peak with increase of its instantaneous magnitude, and capacitor voltage becomes 0 after a quarter cycle of phasor rotation or after t by 4 time instant. And now instantaneous value of capacitor voltage is 0 and instantaneous circuit current is peak positive value, and further rotation and elapse of time reduce current magnitude and increase capacitor voltage, and one complete cyclic rotation will generate one complete cyclic variation of instantaneous magnitude. That means this wave shape diagram and this phasor diagram represent one of the same thing, and capacitor voltage lags circuit current by 90 degree, and RMS magnitude of voltage of capacitor is I times XC, where XC is capacitive reactance given as 1 over omega C. So in a RC series circuit connected to sinusoidal alternating voltage, if we take series circuit current as a reference phasor at horizontal line, the voltage of resistance come along resistance line in phase with series circuit current, and resistance RMS voltage is RMS current multiplied by ohmic value of resistance, V is equal to IR, and RMS voltage of capacitor lags current by 90 degree, and it is along minus JXC line of capacitive reactance, and RMS voltage of capacitor is RMS current multiplied by capacitive reactance XC, where XC is 1 over omega C, and omega is angular frequency of supply, and C is capacitance of capacitor in farad. So in RC series circuit, voltage of resistance and voltage of capacitor got a 90 degree phase difference. Resistance voltage is in phase with current, and capacitor voltage lags circuit current by 90 degree. As per Kirchhoff's law, in this RC series circuit, total applied RMS supply voltage across this RC series in phasor value is phasor sum of voltage across resistance and voltage across capacitor. And we know when current is taken at horizontal reference, the voltage of resistance V equal to IR come in phase with circuit current, and voltage of capacitor V is equal to IXC lags current by 90 degree, and the phasor sum of resistance voltage and capacitor voltage can be obtained when current phasor rotation is freezed at horizontal reference line and voltage of resistance and voltage of capacitor are as shown in their phasor position. And if rotating phasors are freezed, then they are just like vectors, and for vector summation we can put tel of capacitor voltage on head of resistance voltage, and tel of resistance voltage and head of capacitor voltage is phasor sum of RC series supply voltage. And we can say from this right angle triangle the RMS value of supply voltage is Pythagoras sum of voltage of resistance and voltage of capacitor as shown by this Pythagoras relation. Hypotenuse V square is base square plus perpendicular square. So in this right angle triangle, hypotenuse V square is equal to VR square plus VC square, and when we take square root, V is equal to square root of VR square plus VC square, and in place of VR we can write IR, where I is RMS current of circuit and R is ohmic resistance value, and voltage across resistance is I times R. And similarly voltage of capacitor, RMS value of capacitor voltage is RMS current multiplied by capacitive reactance, and when VR is taken as IR and VC is taken as IXC, the total supply voltage can be written like this. And here this common current of resistance and capacitor in series RC circuit brought out, and this expression got this simplification form where RMS voltage become equal to RMS current multiplied by square root of R square plus XC square, and this factor square root of R square plus XC square is given a new name Z known as impedance, and our relation for RMS voltage and RMS current becomes V is equal to IZ. We can say in case of pure resistance our relation is V is equal to IR, in case of pure capacitor our relation is V is equal to IXC, and in case of RC series circuit our relation is V is equal to IZ, where Z is Pythagoras calculation of resistance and capacitive reactance, where capacitive reactance is 1 over omega C. We got similar type of impedance calculation in RL circuit, where Z become square root of R square plus XL square, but XL was omega L and XC is 1 over omega C, and the phasor position of capacitor voltage and inductor voltage are just opposite, but in both case resistance voltage and reactance voltage, whether it is inductive reactance or capacitive reactance, form a Pythagoras calculation set. We can say this Z known as impedance is that property of RC series circuit which oppose flow of current in it and demand proportional voltage for flow of current. The unit or measurement of impedance is same as measurement of resistance or capacitive reactance. All three, resistance, capacitive reactance and impedance, are measured in ohm unit. But the calculation of Z is not simple summation of R and XC, but it is a Pythagoras calculation as explained in these examples. It is very interesting that R operator got only real component, it won't have any imaginary component, and its J part is 0 and it is R plus J 0 in rectangle form and R angle 0 in polar form, and its position in complex plane is as shown by a red arrow, whereas capacitive reactance is minus J type, plus J type is vertical upward direction and minus J direction is vertical downward direction, or X is got angle minus 90 degree, and its vector position is as shown by this blue vector, and the vector summation of resistance and capacitive reactance becomes impedance. And in this right angle triangle, impedance calculation can be obtained by Pythagoras relation, where hypotenuse impedance square is base square R square and perpendicular square XC square, or we can say impedance is square root of R square plus XC square. And interesting thing is, when rotating current phasor is freezed at horizontal reference position, voltage of resistance in phase with resistance is proportional to resistance along R line, and voltage of capacitor lagging current by 90 degree is in the direction of XC line and is proportional to XC, and this R XC-Z triangle can become voltage of resistance, voltage of capacitive reactance and total supply voltage. Voltage phasor diagram RXZ triangle is known as impedance triangle, and VR, VC, V and I relationship is known as phasor diagram. And if one understand impedance triangle, one can easily understand voltage and current phasor diagram. Suppose in a RC series circuit resistance is 6 ohm and capacitive reactance 1 over omega C is 8 ohm, then its Pythagoras calculation will give us Z as square root of R square plus X square, and it is 6 square 36, 8 square 64, summation is 100, and square root of R square plus X square becomes 10 ohm. So for 3 unit resistance, 4 unit capacitive reactance, 5 unit is impedance, 3, 4, 5 combination with multiplier 2. Similarly, in another case, if R is 5 ohm and X is 5 root 3 ohm, it's a combination of 1 root 3. Then as per Pythagoras calculation, Z impedance is square root of R square, resistance square, and capacitive reactance square summation. And resistance is 5 and X is 5 root 3. R square become 25 and X square become 75. Summation again become 100. Square root will fetch 10 ohm. And it's a 1 root 3 2 combination with multiplier 5. So there are certain standard Pythagoras combinations such as 3, 4, 5, 5, 12, 13, 1, 1 root 2 when R and Xc are equal in magnitude. Then Z is root 2 times of R or Xc value. And another popular combination is 1 root 3 2 when R and X got 1 is to root 3 ratio. Then Z is twice of the smaller value. And we can easily predict format of impedance triangle, and accordingly we will get voltage phasor diagram. As told earlier, when rotating current phasor is freezed at horizontal reference line, the voltage of resistance come along resistance line and voltage of capacitor come along XC line, and phasor sum become a simple vector summation, and total applied voltage come along Z line, and we can say phase difference angle between current phasor and voltage phasor, in which current leads voltage by a certain phase angle phi, can be obtained by trigonometry of this right angle triangle. And here tan phi is perpendicular over base or Vc over Vr, and capacitor voltage is Ixc and resistance voltage is Ir. Current I is common, so we can say phase reference angle between current phasor and voltage phasor phi is given as tan phi equal to Xc over R, and we can write Xc as 1 over omega C, and tan phi become 1 over omega Rc. If this circuit is pure resistive, current and voltage come in the same phase, and if it is pure capacitive, voltage will lag current by 90 degree, and if it got both real part resistance and imaginary part capacitive reactance Xc, then voltage lag current by an angle in between 0 and 90 degree, and that depends upon value of ratio of capacitive reactance to resistance. And if Xc and R are equal in ohmic value, tan phi become 1 and phi become 45 degree, and if Xc is more than R, tan phi become more than 1 and phi become more than 45, and if Xc is less than R, tan phi become less than 1 and angle phi will become less than 45 degree. So in RC series circuit, current phasor leads voltage phasor by a phase angle of phi, and that phase difference angle is given as tan phi equal to perpendicular upon base or Vc upon Vr or Ixc upon Ir, or is equal to ratio of Xc over R, or when we substitute Xc as 1 over omega C, it become 1 over omega Rc. So this phase difference phi depend upon circuit resistance in ohm, capacitance in farad, and angular frequency or supply frequency, omega in radian per second or F in hertz. If we take current as standard reference sinusoidal quantity I equal to Im sin omega t, then voltage will lag by an angle phi, and its trigonometric expression is Vm sin omega t minus phi, and Im and Vm got a relation of impedance, and we can say Vm is Imz. And if in place of current as reference, if we take voltage as reference with t0 instantaneous value 0 or V equal to Vm sin omega t, the current will lead that voltage by phi angle, and tan phi is given by this relation, and now the current expression will become I equal to Im sin omega t plus phi. But whether it is current as reference or voltage as reference, in both case current leads voltage and voltage lags current, or we can say in capacitive circuit current leads. The practice of this numerical example will enhance our confidence and understanding level. In a AC series RC circuit, we have given a resistance value is 30 ohm and capacitive reactance is 40 ohm. And if in place of capacitive reactance directly in 40 ohm, if one provide us capacitor in microfarad, we will convert that microfarad value in farad, and will use 1 over omega C formula to get Xc value. In this numerical, we are resistance is 30 ohm, capacitive reactance is 40 ohm, we have to find out impedance, current and phase angle between current and voltage when 100 volt sinusoidal voltage is applied to this circuit. We have to also find out voltage across resistance and capacitor. So we know impedance is Pythagoras summation of resistance and capacitive reactance, or Z is square root of R square plus X square. R is 30 ohm, X is 40 ohm, and when we make Pythagoras calculation, Z comes as square root of 2500 or 50 ohm, and it's a standard 3, 4, 5 combination, and Z become 50 ohm. Now we know in a RC series circuit, RMS current and RMS voltage got a relation V is equal to IZ, or circuit current is I is V by Z. RMS voltage is 100 volt, impedance is 50 ohm, so circuit current is 2 ampere, and current leads voltage by an angle theta, and tan theta is XC by R, or 4 by 3, and tan inverse of that gives us phase difference angle of current phasor and voltage phasor, and current lead voltage by an angle theta, and it is tan inverse 4 by 3 or 53.13 degree. We can also find out voltage of resistance part of RC series circuit, and it is I times resistance value. Circuit current is 2 ampere, resistance is 30 ohm, so it is 60 volt in phase with current. And similarly, voltage of capacitor VC is IXC, XC is 40 ohm, current is 2 ampere, and capacitor voltage is 80 volt, lagging current by 90 degree, and phasor sum of resistance voltage 60 volt and capacitor voltage 80 volts comes as total supply voltage 100 volt. We hope this simple and beautiful learning video has explained each and every study aspect of RC series circuit in alternating current supply. Now you understand what is impedance as Pythagoras calculation of resistance and capacitive reactance, and by what angle current leads voltage in RC series circuit, and tan phi of that phase difference angle phi is given as XC over R. Our other learning video of the same playlist are equally useful, and other playlists are also useful. And if you need doubt clearing online classes or exam centric notes from this channel, do join our YouTube membership. Happy learning. Thank you very much.